I went straight to the data the moment it arrived from the PRL team at Mount Abu. No introductions, no preamble, just the raw signal of a visitor whose trajectory had already rewritten the boundary lines of our cosmic neighborhood. From November 12th to 15th, the 1.2-meter telescope perched at 1,680 meters on Mount Abu had captured a series of frames and spectra from the interstellar comet 3I/ATLAS as it slipped away from the inner solar system, its passage past perihelion already behind it. What struck me first was not the strangeness of the object, but the familiarity. I had expected the signature of an outsider, a wanderer sculpted by a distant star's chemistry, but the initial imaging revealed something almost intimate, a coma nearly spherical, bright, coherent, and unmistakably similar to the coma of solar system comets we've catalogued for decades. The coma was the first clue, a luminous exhalation of sublimating ices responding to sunlight, expanding outward as if the comet were breathing into space. Even before I read the accompanying notes from the observers, I could see that its geometry was influenced by our vantage point. Any dust tail, if present, was oriented directly away from us, trailing behind the nucleus from Earth's line of sight, effectively hiding itself. The team had noted the same. Detection of a dust tail would require deeper multiband imaging and ideally a darker stretch of sky once the comet drifted into less crowded celestial territory. Still, that glowing sphere, the coma, told me everything I needed to know about the comet's current state. It was active, shedding material, and interacting with sunlight in a way indistinguishable from the behavior of a local comet. But the images were only the surface. The real revelation lay in the spectra recorded just before dawn, when atmospheric interference was low and the comet rose clear enough for clean photon capture. I opened the spectral files with the anticipation I imagine early biologists felt when slicing open a new specimen, not with hope for something familiar, but with readiness for the unexpected. Yet what appeared was a triad of molecular signatures I knew all too well. CN, C2, and C3, cyanogen, carbon dimer, and tricarbon. Their emission bands flared in the short wavelength region, clean and bright, the chemical fingerprints of volatile ices breaking apart under solar radiation. To grasp the implications, I zoomed in on the CN band at 388 nanometers, then the C2 swan bands, then the fragile, transient C3 signatures. All present, all clear. It's one thing to claim a comet is interstellar because of its trajectory, but another to discover that its chemistry, the very materials locked in its nucleus since its formation, mirrors the inventory of comets born beside our own sun. If 3I/ATLAS came from a distant star system, that star must have forged molecules under conditions similar enough to ours to produce these same reactive carbon compounds. Once again, the cosmos hints that the processes that shaped us are not rare, not aberrations, but universal rhythms echoed across light years. The activity rate of the comet was the next piece. The PRL team had estimated a gas production rate of roughly 1 × 10 to the 25th molecules per second, a level entirely consistent with mid-sized solar system comets under similar thermal conditions. No signs of hyperactivity, no signs of suppression. Just a comet behaving like a comet. That single measurement carried weight. If an interstellar object displays the same outgassing profile as local bodies, then the underlying physics is shared. Heat hits volatile ice. Ice sublimates. Gas expands. Molecules fluoresce under sunlight. The dance repeats across galaxies. I felt a strange satisfaction reading that number. Too often the public imagines interstellar objects as exotic, alien things, fragments of unimaginable physics or technology. And though the potential for technological artifacts is a valid scientific question, data like this is a grounding reminder. Most of what passes between stars is natural, not unfamiliar, not incomprehensible, simply matter obeying the same laws everywhere. But the story wasn't finished. The scientists had plans to follow 3I/ATLAS as it drifted into darker skies, where the tail, especially any ion tail, might be detectable with deeper exposure and multiband imaging. Ion tails can reveal the interaction between solar wind and cometary gases, and if detected, their curvature or orientation can sometimes indicate past bursts of activity or changes in outgassing. The Mount Abu telescope, though only 1.2 meters, has proven itself capable not only in studies of comets, but of exoplanet atmospheres, variable stars, and high-energy sources. With 3 I/ATLAS moving toward a cleaner backdrop, the next phase of observations could uncover structure previously hidden, maybe even asymmetry in the coma that hints at jets or rotational effects. I reviewed the November imaging again, this time focusing on subtle gradients in brightness. The coma was strikingly symmetric, suggesting that at least during those observations, the nucleus wasn't undergoing violent jetting. That alone was noteworthy. Some comets erupt irregularly, releasing bursts of gas that distort the coma and create spirals, plumes, or sharp brightness edges. 3 I/ATLAS seemed calmer, more uniform, a steady release rather than sporadic sputtering. This stability likely contributed to the clarity of the spectral readings. A predictable, even outgassing pattern produces consistent molecular populations in the near nucleus region, which simplifies interpretation. As I cross-referenced the spectra with archival comet data, the overlap was undeniable. CN radicals glowing in ultraviolet, C2 molecules producing greenish emissions, 3 contributing faint structures in the blue. These aren't rare. They are textbook signatures. And that was the twist that kept me leaning forward. An interstellar comet formed in the cradle of a foreign star system carries the same chemical song as the icy remnants of ours. Differences must exist, perhaps in isotopic ratios, dust-to-gas ratios, or microstructure of grains, but none of those were evident yet. The more I studied the report, the more I felt the boundary between ours and theirs dissolving. Chemistry is a universal language, and this comet was speaking it fluently. The cosmos, once again, was reminding us that the bridge between star systems is not built of metal or fantasy. It is built of shared origins, shared physics, shared molecules drifting across the dark. That was only the beginning. I went back to the raw spectra the following morning, long before sunrise, wanting to see if my initial impressions still held under sharper scrutiny. They did, but they also deepened. The pre-dawn light at Mount Abu had given the PRL team a narrow but precious window where the atmosphere settled just enough to permit clean detection of fragile molecules. CN, C2, C3, each one a relic of primordial chemistry, had survived billions of years locked inside the comet's nucleus before sunlight coaxed them into fluorescence. As I scrolled through the wavelength plots, I kept returning to the idea that 3I/ATLAS was not an anomaly but a messenger. It wasn't here to confuse us, but to confirm something fundamental, that the building blocks of comets across star systems follow similar chemical pathways. The CN band was my anchor. That sharp emission spike at 388 nanometers appeared with the confidence of a signature long known to cometary science. CN radicals are fragile. Sunlight breaks them apart quickly. Yet here they were, abundant enough to shine clearly in the spectrum. Then came the swan bands of C2, glowing with the greenish intensity we see in many solar system comets, and the faint, fleeting C3 signatures, whose presence often indicates deeper layers of carbon-rich material being exposed by sublimation. These weren't random traces. They formed a coherent pattern, a chemical identity card stamped with familiarity. I imagined the nucleus rotating slowly, sunlight sweeping across pockets of ice that hadn't been warmed in perhaps millions of years. The energy input breaks molecular bonds, releasing radicals that then dance in the coma before dissipating. If the comet had been inactive or exhausted, these emission bands would have been faint, smeared, or absent. Instead, the lines stood out with surprising vigor, reinforcing the idea that this interstellar visitor still carried a reservoir of volatile material comparable to our own long-period comets. Yet what fascinated me even more was the estimated rate of gas production, 10 to the 25th power molecules per second. A number like that isn't just a measurement, it's a declaration. It's the comet saying, I respond to starlight the same way your comets do. The PRL team had computed the production rate using standard models of fluorescence efficiency and line intensity, methods refined over decades. The fact that 3 I/ATLAS matched typical solar system behavior so closely meant that its outgassing wasn't enhanced by exotic chemistry or suppressed by unusual composition. It was ordinary in the most extraordinary way. As I thought about that production rate, I pictured the nucleus, a chunk of ancient ice and dust, likely tens or hundreds of meters across, losing mass steadily as it fled our inner solar system. In a star system far from ours, long before it was ejected into interstellar space, similar sunlight would have triggered similar sublimation. The laws governing phase transitions don't care which star you belong to. Heat a volatile, it vaporizes. Blast it with photons, it fluoresces. The universality of these processes was written into every emission line in that spectrum. I reviewed the imaging files again, this time pushing the brightness curves to amplify faint structure in the coma. No irregularities, no clear asymmetry. That near-perfect circular envelope meant one thing: stability, a steady, uniform outflow of gas. Many comets we observed display jets, narrow plumes caused by localized vents or fractures on the nucleus. Jets create spiraling structures, brightness gradients, or distortions in the coma. None of that appeared in the PRL images. 3 I/ATLAS seemed almost serene, as though its internal structure allowed for an even release of volatiles across its surface. That uniformity simplified everything. We weren't dealing with a chaotic, eruptive object, but with a calm wanderer, shedding mass in predictable patterns. Still, what the images didn't show was just as intriguing. The dust tail, if present, lay hidden behind the comet from our perspective. Dust grains, pushed by radiation pressure, stream away from the sun, forming tail structures that can reveal the age, density, and activity level of the nucleus. But from Earth, the geometry was aligned such that the tail lined up perfectly behind the nucleus, invisible without deeper exposure. I read the team's note about needing multiband, deep imaging in darker skies, and I could feel their anticipation. A tail isn't merely decorative, it's a diagnostic. An ion tail, especially, interacts with the solar wind, tracing magnetic field lines and revealing patterns of plasma dynamics. If detected later, it could offer a rare opportunity to study how interstellar cometary material behaves in our sun's charged environment. The Mount Abu telescope, modest in size but powerful in capability, had already proven its worth repeatedly. It had captured exoplanet transits, variable star oscillations, and emissions from high-energy cosmic sources. With 3 I/ATLAS moving into a region of sky with less background light and fewer bright stars crowding the frame, the PRL team stood on the threshold of new revelations. As I considered the next steps they outlined, deeper exposures, expanded spectral range, attempts to isolate faint ionic lines, I felt the edge of excitement that comes when science pushes against the unknown with precise instruments and steady hands. The more I studied the data, the more one theme kept emerging: sameness across distance. When the first interstellar objects, Oumuamua, then 2 I/Borisov, now 3 I/Atlas, entered our solar system, the question wasn't simply what they were, but whether they were fundamentally different. Yet once again, the evidence pointed in a different direction. Across the gulf between stars, the same volatile compounds form in cold environments. The same photochemical reactions light up cometary comae. The same outgassing behavior emerges under stellar heat. Each spectrum was like a whisper from a distant system saying, "We are not as far from you as you imagine." And in that whisper I felt both the vastness of the universe and its quiet unity. I spent the next evening confronting a question that lingered beneath every line of data. Why does an interstellar comet look so ordinary? The idea kept looping in my mind as I reviewed the gas production estimates again. 10 to the 25th molecules per second, an emission rate that could have come from any number of solar system comets we've studied for decades. That number made 3 I/ATLAS feel less like an alien visitor and more like a distant cousin, shaped by familiar processes under a different sun. I found myself replaying the Mount Abu observations in my head, imagining the team working through the pre-dawn cold, capturing photons that had traveled millions of kilometers, only to deliver this message of cosmic continuity. But stability does not mean simplicity. The comet's nearly perfect spherical coma hinted at a nucleus that released volatiles uniformly. Yet I knew that deeper within that symmetry lay complexity we hadn't uncovered. Jets might be absent in the images, but their absence could mean several things: a uniformly active surface, a nucleus still warming evenly after perihelion, or even a rotational state that distributes heat in such a way that localized bursts smooth out over time. The geometry of the coma wasn't merely a matter of shape, it was a clue to the internal physics of the nucleus. I zoomed back into the spectral signatures, staring again at the CN band, as if the more I looked, the more the comet would reveal. CN radicals don't survive long in sunlight, so their presence means they're being continually replenished. That implies ongoing activity, not just residual sublimation from earlier in the comet's path. The C2 and C3 bands reinforce the idea. Rich carbon compounds breaking apart, recombining, and glowing in the visible and ultraviolet spectrum. Each line represented a molecular ancestor forged in the early history of a distant star system. When I thought of the comet as a time capsule, the familiarity of these molecules became even more haunting. Two star systems, separated by light years and shaped by different histories, still found their way to the same chemical pathways. This symmetry in chemistry led me to a larger thought. Maybe the universe has far fewer surprises in its cold, dark edges than we expect. Cometary material forms in protoplanetary disks where temperatures drop low enough for volatiles to freeze. Given that carbon, nitrogen, and hydrogen are abundant across the galaxy, the chemical recipes may simply converge. Perhaps every young star system writes the same notes into its icy bodies, producing comets that follow a universal pattern. If so, then interstellar comets are not unique oddities. They're ambassadors of a shared galactic ancestry. Still, the Mount Abu telescope's plan for deeper imaging remained crucial. The hidden dust tail bothered me, not because it was missing, but because it was concealed by geometry. A dust tail reveals much more than the presence of dust. It encodes the momentum of particles, the timing of outbursts, and the interaction between the nucleus and the solar radiation field. A faint, invisible tail might simply align with our line of sight, but a detailed multi-band exposure could tease out subtle gradients in brightness or delicate curvature in the coma's edge, betraying the tail's true direction. Dust is the memory of a comet's activity, and without that memory, our understanding remains incomplete. The PRL team's plans extended beyond imaging. An ion tail, if detected, would interact with the solar wind in ways that solar system comets have taught us to read. Ion tails, composed of charged molecules like CO plus or H2O plus, are shaped by magnetic fields rather than radiation pressure. Their alignment, curvature, and diffusion reveal not only the comet's internal chemistry, but also the condition of the solar wind at that moment. If 3I/ATLAS displayed an ion tail, even faintly, it would give us a chance to compare how interstellar material interacts with our star's plasma environment. That alone could offer insights into how long this comet has been wandering, how its surface has evolved, and how its volatile inventory has survived its long journey. I pictured the comet now, drifting outward, leaving the sun behind, slowly cooling as it climbed toward darker, emptier regions. The further it traveled, the more challenging the observations would become, but also the cleaner the sky. Less glare, fewer bright stars, clearer isolation of its faint emissions. The ideal window for observing subtle features often comes after the comet has passed perihelion, once the chaos of solar heating has quieted into predictable decline. That was the window the Mount Abu team sought. As I considered the implications, I realized that Every detail we collected, every molecule, every photon, every estimate of gas production helped build a bridge across interstellar space. Even the ordinary nature of the comet was extraordinary. It meant the physics of ice, dust, and sunlight were universal. It meant other star systems froze their ices at similar temperatures. It meant chemical evolution followed comparable paths. And it meant that the universe is not fragmented into small pockets of unique processes, but unified by shared laws. The idea brought me back to a familiar thought. If cometary chemistry is consistent across systems, then the ingredients for life, carbon chains, nitriles, hydrocarbons, are also consistent. Comets are often delivery systems of complex molecules to young planets. If interstellar comets resemble ours, then star systems across the galaxy may have seeded their planets with the same building blocks. I sat back from the screen, absorbing the weight of that. 3I/ATLAS wasn't merely an icy wanderer, it was a sample, an accidental sample of another system's history. And in that history, I saw an echo of our own. The comet was ordinary, yes, but ordinary is exactly what makes it remarkable. The universe, it seemed, was telling us that we belong to something larger, something continuous, something shared across light years. And 3I/ATLAS was the messenger carrying that quiet, cosmic reassurance. I kept returning to the notion that 3I/ATLAS was still only partially revealed to us. The coma, the spectra, the gas production rate, they formed a compelling foundation, but the fuller character of the comet remained hidden behind geometry, distance, and the limits of a pre-dawn sky. The Mount Abu team understood this deeply, which is why their next phase of observation focused not on what had already been seen, but on what had yet to be uncovered. As the comet drifted into darker sky regions, away from the brightness of crowded stellar fields, its faintest structures might finally separate themselves from the background. I imagined it. A faint ion tail emerging, stretched thin and pale blue, pointing directly away from the sun, betrayed only by long exposure imaging. Ion tails are fragile. They require ultra-clean conditions to detect, especially when dealing with an object as distant and dim as 3I/ATLAS. The PRL team aimed to push the 1.2-meter telescope to its limit, cycling through multiple bands, stacking exposures, teasing out the subtle fingerprints of ions interacting with the solar wind. Those ions would be remnants of molecules that had just been liberated from the nucleus and then stripped of their electrons by sunlight. In the clean, high-altitude air of Mount Abu, with longer integrations, there was a real chance of isolating these signals. And if they succeeded, it would provide not just more data, but an entirely different lens through which to interpret the comet's behavior. The ion tail, if present, would reveal the flow of plasma around the comet, the structure of the sun's magnetic field lines in that direction, and whether the comet had undergone any sporadic activity since the last observations. Unlike the dust tail, which tracks momentum and size distribution of grains, the ion tail was a live map of the comet's immediate environment. It would tell us whether 3I/ATLAS had responded to solar wind pressure in ways typical of solar system comets, or if its behavior suggested a different balance of volatiles and ionized species. In other words, it could highlight the subtle differences that the Coma and spectra had not. But even as I considered the significance of the unseen tail, I found myself thinking about the telescope itself. The Mount Abu Observatory isn't a giant, but its track record is formidable. Over the years, it has captured transit dips of distant exoplanets, mapped light curves of variable stars, and recorded emissions from high-energy astrophysical sources. Each of these achievements required precision, patience, and the ability to extract signal from noise, qualities essential for the study of comets. The team knew how to work with faint objects. They knew how to stretch exposures, adjust filters, and control for atmospheric noise. That experience gave me confidence that their follow-up observations could reveal what the earlier ones had not. I pictured the comet slipping further from the sun each day, its surface cooling as it retreated from the heat that had roused it. The gas production rate would decline gradually, but during this transition, the tail might become more defined. In some comets, the decrease in volatile sublimation causes the dust-to-gas ratio to shift, making dust tails more pronounced. In others, ion tails sharpen as the coma thins. With 3I/ATLAS following an outbound trajectory, this was the moment to catch those subtle transitions. The PRL scientists seemed aware that the comet's quiet facade might conceal rapid internal changes triggered by the loss of solar heating. The symmetry of the coma, so stable in earlier images, might also begin to change. As the nucleus rotates and cools unevenly, fractures can stiffen, vents can close, and sublimation can become patchy. That patchiness can disturb the coma's shape, introducing gradients or slight asymmetries. If deeper exposures revealed such features, they could map the comet's rotation, its active regions, and the distribution of its surface ices. Even without direct imaging of the nucleus, which is too small and distant to resolve, the coma can act as a proxy for internal processes. This is what I found so compelling about the observational plan. They weren't passively waiting for the comet to brighten or flare. They were preparing to detect the faintest hints of change, the small deviations from uniformity that could speak volumes about the comet's structure. They were treating 3I/ATLAS not as an outsider, but as a scientific equal to any well-studied solar system comet, subject to the same methods, the same scrutiny, the same models. That parity mattered to me. Too often, interstellar objects are framed as curiosities, their value limited to their foreignness. But the real value lies in comparing them directly, methodically, and fairly to what we already understand. The deeper I sank into the data and plans, the more I realized something. The significance of the observations was not that 3I/ATLAS resembled our comets, but that we were finally treating interstellar comets as part of a broader cosmic continuum. The moment we regard them not as special cases, but as natural extensions of the same physics, we gain the clarity needed to distinguish real anomalies from ordinary behavior. And so far, 3I/ATLAS displayed nothing anomalous, only universal chemistry and universal processes playing out across billions of years and billions of kilometers. By the time I finished reviewing the data, 3I/ATLAS was already too faint for the Mount Abu telescope to study further. It would continue outward, eventually passing beyond the influence of our sun, returning to the interstellar dark that had shaped it. But its passage left an imprint not just in the data, but in our understanding. We may never see it again, but in its brief visit, it bridged the space between solar systems with nothing more than the quiet glow of sublimating ice. I closed the files knowing the comet had given us exactly what we needed. Not spectacle, not anomaly, but connection. A reminder that the laws governing distant worlds are the same ones that govern ours. A reminder that the universe is built on shared patterns, shared chemistry, shared origins. 3. I/ATLAS arrived as an interstellar stranger. It left as proof that the stars speak the same molecular language.